two topics. One is about construction principles for modular forms and examples for this, and the second topic will be derivatives of modular forms. But before I do that, I want to say something about cusp forms and non-cusp forms. So gamma can be now an arbitrary subgroup of finite index. Okay, so what is the space of cusp forms? Now this will again be a modular form for some group conjugate to gamma, and it also is periodic, and it has a Fourier expansion which goes over positive semi-definite matrices. So it has a Fourier expansion supported only on okay, in degree 1 it means that your Fourier coefficient, your Fourier expansion in all cusps has just has only 0 as constant coefficient. So it coincides with the usual definition. And this condition these conditions SP and Q, but if you change it from the left by gamma, then evidently nothing changes. But you can also change it from the right by something that we call SPNQ infinity, where SPN infinity is AB0 and D. So C is equal to 0, and then you can act on the Fourier expansion itself, and this condition is not changed. So this is a finite condition. And if you don't like SPNQ, well, every element of SPNQ can be, by changing it by an element of SPNZ, can be made into an element of SPNQ infinity. And therefore this is the same as gamma SPNZ, not SPNZ infinity, so you do not really need rational matrices here. Okay, there's another description of this which will be important later. So we can associate to f a function phi f of z star, which z star is in hn minus 1 by the limit of f z star 0 0 it t goes to infinity. And we can do this not only for f but also for f slash gamma. This is again a modular form for and now we can describe the m and rho of gamma cusp is an phi of f rho gamma is just the zero function. And we are left with a problem to describe a complement of the cusp forms. How do we do this in degree 1? Well, to each cusp we can associate an Eisenstein series where the Fourier expansion in that cusp has a non-constant zeros term. And so all modular forms, in the case of elliptic modular forms, can be written as cusp form plus sums of Eisenstein series. Now, if we want to do this here, we will have a problem because we do not have just constant functions, but a lot of these kind of images of phi operators to be considered. So m and rho cusp forms, well, and these things can be iterated here. Yeah, you can apply this kind of phi operator again, and finally you will end up with something where you cannot continue like that unless you get 0, and those will be cusp forms of lower degree. So cusp forms of lower degrees of possibly all lower degrees will enter here. So it will be rather complicated. I will say something later how this will actually happen, how we can get modular forms in this complement from cusp forms of lower degree. Actually, which kind of things appear, this is a little bit vague what I wrote about the rho prime here. If rho is just the power of the determinant, it will be the same. It will still be the same power of the determinant coming up here. But if rho is a general polynomial representation, then there will be some obstructions occurring. I'll give you an example here. I don't know whether I mentioned this before. M and rho gamma is equal to m and rho gamma cusp if rho corresponds to something where the highest weights all satisfy strict equalities. So not only the type of gamma will enter, but also the nature of rho will enter, and sometimes there will be no non-cusp forms at all, independent of gamma. Okay, so this just I need this description later. Now I come to examples and constructions of modular forms. What do I do? Okay. Now, I think Alexei mentioned that he will use Rankin-Selberg method, and that theta series will enter. So I will give you the first example, actually the first very simple example. There is no convergence problem, and so on. The theta series. So we fix some s positive definite integral size m. Remember, half integral means the entries on the diagonal are integral, and outside of the diagonal 2 times the entries is integral. And now we can define theta series like this. I trace of now B transposed as B times Z. Now this matrix here is again n by n, so it makes sense to multiply them and to take the trace. And if you write down a Fourier expansion of this, and this is the number theoretic meaning of this, we have this T and n by n half integral matrices, positive semi-definite A of S T and this A of S T is just the number of solutions of a quadratic equation BT S B is equal to T. No? This is what people in the arithmetic of quadratic forms call representation numbers of the quadratic form T by the quadratic form S. Yeah? So if n is equal to 1, we are talking about, say, how often you can write a number as a sum of, I don't know, 21 squares or something like that. Depending, of course, also on the nature of this S. So, and this is now an example of such a modular form for some gamma. And this gamma depends on the so-called level of the quadratic form. It can be described very precisely. Let me shortly write down some advantages. Series, so the Fourier coefficients are all integral. Of course, they are numbers of solutions of some equations. There's no danger that you construct a zero function. And actually, in many cases, one can show that you can really get all the modular forms in this way. This depends on gamma and depends on the weight. So I just write this in brackets. Sometimes it will not be true for arbitrary congruent subgroups, but say if you have the square free level, you have a good chance with high weights to, if m over 2 is large, to get all modular forms. Okay. You might say, what about arbitrary row? This was just about, this is det m over 2. So to include well, what are pluriharmonic polynomials? First of all, they are polynomials which start from such a matrix space and go to this representation space V with maybe I have to take pluriharmonic means they satisfy certain equations under generalized Laplace operators. And now you look at theta n as p of the to be I did B, yeah, okay. Now we have to insert here the square root of this quadratic form S, and again, and then this is an M and rho tensor that m over 2 of gamma. But now the thing is much more complicated concerning the non-vanishing. These things can be zero, and this is not so easy to describe. In any case, this is a simple construction principle for a lot of modular forms. And maybe this is called basis problem. This is the question whether you can get all the modular forms from such theta series attached to quadratic forms. Of course, you have to vary the quadratic form then. Okay. Yeah. And these things will come up in Alexei's talk in his Rankin-Selberg method. Now I come to a basic construction principle. And this construction principle goes by brute force. How is it? Phi to be you start from any holomorphic function, and this is of course not a modular form, but how can you create a modular form out of this? Well, modular forms satisfy some symmetry conditions. And how do you get from an even function on the real line, from an arbitrary function on the real line, how do you get an even function? You take f of x plus f of minus x. Yeah? And this we will do here by averaging over gamma. Huh? So of course, rho, since I go to this representation, rho is again representation. So, and now p rho n of phi of z, I leave here some place, open place, will be just defined by phi slash rho of gamma, gamma, and gamma. If everything converges, then this will be, if it converges nicely, say locally uniform or something, then it will produce some holomorphic function, and it will have this requested transformation property. Yeah. So, but to improve, the problem will be convergence, depending on our function phi. But certainly we cannot satisfy convergence if infinitely many if phi is already invariant under some subgroup. Yeah? So we should divide out some subgroup for which phi is already invariant. Yeah, this does not guarantee convergence, but it improves our chance to get something. Yeah? So this is an m and rho of gamma Okay, and we have already done this. This is nothing. This principle is nothing new, because even the way in which I defined the Hecker operators fits into this. Of course, there I took as phi. I took e.g. definition of fits here. Phi was f rho delta, Hecker operator t delta, and gamma was gamma prime was gamma intersected delta inverse gamma delta, and the summation was finite. Yeah, but this is only a side remark. So, first example. The most stupid function you can think of is just the function 1. So we are in the scalar valued case. That L what does it mean? It means determinant Cz plus d to minus L is 1. Yeah, identically 1 in Z. This means Z is 0 and determinant of d to the L is 1. And this Pn, let me follow this notation, determinant to the L of 1. So yeah, and gamma prime, this is just the sum of determinant of Cz plus d to the minus L, where Cd is in our gamma modulo gamma prime. And this is something that it was at the beginning of the whole theory of Siegel modular forms. This is the Siegel-Eisenstein series. And well, if L is odd, we have a slight problem. Everything is well defined, but the series will not be very interesting. It will just be 0, because everything will appear together with the negative of it. at least for SP and Z. If we choose the group small enough such that determinant of D is plus 1 anyway, then it's different. So one has to be careful. Sometimes here terms can appear together with their negative, and then everything will be 0. So we'll have to look at just at the even case. But let me emphasize that this statement that the Fourier coefficients are rational with bounded denominators, well, it cannot be deduced, or should not be deduced from the general statement which I gave last time. Of course, that the Fourier coefficients are rational, one has to compute. But the boundedness of the denominators we should compute directly, because the general theorem of last time will be deduced from this. Yeah. So A of t, so A of 0n is just 1. L even. So and now I take just the positive definite matrices, and this means I leave out something in between, non-zero t's for which the determinant is equal to 0. Those can be reduced to the case of lower degree. A of t is of Riemann zeta functions minus 1. I think this was already at in Alexei's talk. And then there is a product of p dividing determinant of 2t and some polynomials fp p to the minus k. This is some polynomials. So these are elementary expressions here. But then this time is 1 if n is odd, and it is L of k minus n over 2 with a quadratic character associated to t if n is even. So now say this is true if determinant of 2t is square free. Otherwise, formulas are finite sums of such things. But from these properties you can read off that it's rational with bounded denominators. And it, of course, it includes the case of the degree 1, where it was 2 divided by zeta of 1 minus k times divisor sums. No? Now, it took a long time to come up with this formulation. Siegel himself, he proved this statement here, but not in this explicit form. But it took a long time until into the 1980s to come up with this kind of formulation here. Okay. So, but this is also some basis for the p-adic interpolation, because these things carry Kummer congruencies. Yeah? So, the next example would be, remember we just need functions phi. And the functions p and still stick to determinant this phi and the corresponding gamma prime. This gamma prime now depends on the rank of t. So this is something like gamma prime. And this is something people call Poincaré series. They generate the full space. If t runs over everything here, and if t is equal to 0, this is just Eisenstein series. Nothing but Eisenstein series. But in general, if t, t, what is t? Yes. Sorry. But in general, the Fourier expansion is very bad. It consists of infinite sums of Klosterman sums times Bessel numbers, some Bessel functions. When I say it's very bad, it's not so bad from the point of view of analytic number series. They can handle this. Yeah. So I have to apologize to all people who are happy with Bessel functions, and in particular with Klosterman sums. But it's not that you can prove. You cannot prove that they might have algebraic Fourier coefficients. It's highly transcendental. Okay. Yes. There's some remark I want to make. Why did I so far only consider scalar value things? I mean, this construction which I wrote down was valid for arbitrary rho. So you can ask, why didn't I write down Siegel-Eisenstein series for arbitrary rho? So suppose that rho is not that to the L, and you take any f in I claim that, well, the Siegel-Eisenstein series had the property that the constant Fourier coefficient was different from 0. Huh? And now, if I take this f with a f of t say gamma, maybe it's P and Z, but this works also for congruent subgroups. If rho is just the determinant, this is not a problem at all, because u0 u minus transpose t is in SPNZ, and so you can plug this into the Fourier expansion, and then you get this invariance property. Now, how? When you apply this to t is equal to 0, it means that AF of t, which is 0, is equal to rho of u AF of t for all u. Yeah? And this cannot happen unless this element of your representation space is equal to 0. Yeah? It just has too many invariance properties. Yeah. So the constant term of a vector valued modular of a truly vector valued modular form is 0. Therefore, it doesn't make any sense to look for vector valued Eisenstein series. No vector valued Siegel-Eisenstein series. This is just the tip of an iceberg of rather subtle statements about necessary conditions on rho to be satisfied in order to get modular forms with non-vanishing Fourier coefficients of certain lower rank. I made a statement before that if the highest weight k1 to kn satisfies strict inequalities everywhere, then we have just cusp forms. This was also a kind of such statement, but it's too complicated here to write down the general statements. They give conditions roughly on the number when you look at this highest weight k1 bigger or equal to k2 and so on, how many times equality appears among the integers in the highest weight. Yeah? But this is a lot of things come from invariant theory. Yeah, one has to take care of that. Okay, but this.
Where one could find these statements?
Pardon?
Where one could find these statements?
Yes, there is in fact a full paper on this by Weissauer in 1983 on vector valued modular forms. You can find precise statements on this. And I just gave you now two examples. One was an example about the cusp forms, and the other one was about modular forms with non-zero constant Fourier coefficient. But this is just two extreme examples. So we need strict conditions, but as long as you do not worry about vector valued modular forms, it is okay. So here's a third example. Any number r between 0 and n. Now we start with a cusp form. MR rho over gamma. How do I do this? Let me see whether I start with vector valued right away, or do I first maybe I do it for the scalar valued case first. Sorry. Now, maybe I called it phi, yes? No, this is still f. Sorry, now, this is f. I take it as a cusp form. This is mainly for ensuring to show convergence. And now, the upper left block of a matrix in the Siegel half space is itself in HR. And I can take this. So, and what is my Pn bit L of, well, phi gamma prime? This is then just the sum over gamma in, say, no, gamma, what gamma prime, determinant C set plus D to the minus L. I take my F, I apply gamma to Z, and then I take the upper left block of what has arrived from this. Huh? And indeed gamma prime, this is nothing but gamma intersected with C and R, with C and R is the set of all. I can write it in terms of algebraic group. G is equal to this is n plus r, and this is r, n minus r. Yeah. So the last n plus r rows and the first n minus r columns are 0. This is clear up to convergence, and the convergence condition is L is bigger than n plus r plus 1, and this runs under the name Klingen-Eisenstein series. And if you wish, you can include the Siegel-Eisenstein series as a degenerate case. Here r is equal to 0. If r is equal to n, this is just you do nothing. Yeah, you reproduce your original cusp form. Why do I introduce these? So, what can we say about the Fourier coefficients? Well, maybe I tell you a short story now. I got my PhD from Klingen, and I suggested to him to write my PhD thesis on the Fourier coefficients of his Eisenstein series. And he said, well, if you want to do, I gave up. I could not do this. And I don't tell you this because I want to claim that I am much. But then I came up with a special case, n is equal to 2, the smallest possible case, starting from a cusp form of degree 1. And I showed him my result, and he was very disappointed. I had to convince him that it is a reasonable result, because what was expected at that time, when you just write down these things, that the Fourier coefficients will be finite sums of the Fourier coefficients of the modular form from which you start. Just as you have in the Siegel-Eisenstein series case, you have essentially you have finite sums. So what people expected was that the Fourier coefficients of these Eisenstein series are just finite sums of the Fourier coefficients of the cusp forms. You start with finite sums, which would naturally give you all kind of algebraicity results, starting from your cusp form of lower degree. But already in degree 2, the result was completely different, actually. So first, if t is equal to t1, 0, 0, 0, and t1 is in lambda r positive, say now gamma is SPN Z. then A of t is just AF of t1. So you get back.
Before the congruence modular principle you studied.
Pardon?
It was before you studied congruence modular.
Yeah, that was before. I could do that only after I had the formulas. Yeah. So in the low rank, in the lowest possible rank, you get back these three coefficients, which you had from the modular form of degree r. But now let's take t to be in lambda n. So and first of all, it will be an infinite sum. It will be an ugly infinite sum, unless you assume that you start from a Hecke eigenform. When you start from a Hecke eigenform, you can write it in a nice way. So, and assume that f is well, I ignore some factors. And I write the quotient of two infinite sums. A minus r plus 1, and the sum is over all b in okay, I can do this. Yes. V and R modulo GLR Z, and well, some rank conditions such that this determinant is different from 0. And in the denominator, just the value of one of the L functions which we introduced before appears. This is a standard L function which I defined last time, and it is at the point k minus r times some elementary factors. To tell the full truth, this is only correct if t, again, if square free, otherwise you get more complicated things. Now, my PhD advisor didn't like this formula. As I said, it was just for degree 2. And I had to convince him that it is reasonable. Well, why is it reasonable? Because one can they share the same transcendental factor. So the quotient is algebraic, no? Namely, what is the joint transcendental factor? It is some power of pi, which doesn't matter, it's the same power of pi, times something which we have not introduced yet, namely Peterson product of f. Peterson. No.
Denominator doesn't depend on t, only numerator. Yeah?
Only numerator depends. Yeah. Denominator does not depend on the matrix.
It's like universal transcendency.
Yes, this is universal. The denominator is universal, and the algebraicity of the numerator you can get by Rankin-Selberg method. Yeah. Not its algebraicity, but algebraicity up to Peterson product. So it's a quotient of two interesting data. Yeah? The denominator is the value of a L function. And so it fits into the Langlands program. The numerator does not have an Euler product. Yeah? It does not have an Euler product. This comes from the fact that here you could make a resummation such that representation numbers would come up. Representation numbers times the Fourier coefficient. It's a Rankine convolution, yes. So in that sense it fits into Dirichlet series of modular forms. Yeah, but it is not something corresponding to a Langlands L function, not at all. But I think nowadays everybody is convinced that this is a reasonable, interesting formula, and I got my PhD from this. So, but yes, so this is one of the cases where we can compute Fourier coefficients of such of any Siegel modular forms, and it has more properties even. So if you it is compatible with the action of the Galois group. If you start from your cusp form, last time I said that you can start from a cusp form and apply some sigma in the automorphism group of C, yeah, to it. And if you compare the construction for F and F for F sigma, then also just these values will change. Yeah. And if you want to write this in a linear way, that is not for eigenforms but for arbitrary modular forms, it is a terrible formula. Yeah, it only becomes smooth and understandable by this quotient, because after all, you can only understand it if you look at it as a quotient of two things which are well known. You know? Okay. One remark here. maybe 0 I have to include the Ziegler-Eisenstein series. And this is the way we get everything that is not cuspidal. It comes from a cusp form of lower degree, and we take these Klingen-Eisenstein series to get something of degree n, and all of them together they generate the space of non-cusp forms. Okay. Yeah. So I have here some remark about the vector valued case, but I omit this now. Now I come to the second topic, namely derivatives. How much time now? Let's see. Let's look at a very simple example. You take f, h to c, so f so, and if you take the derivative, then you get f prime of z. Now, the inner derivative of z goes to az plus b divided by cz plus d is c divided by cz plus d to the square. So you get c k plus 2 plus so everything would work only if k is equal to 0. We definitely don't get a modular form again by these derivatives unless so the derivative of j function satisfies an appropriate transformation property, but otherwise nothing happens. And this is typical. We can say quite generally that in most cases, derivatives of modular forms do not give modular forms except for a certain set of weights, very few weights. Yeah, there's some research going on now on determining exactly in a most general context for which weights actually it happens, but in general it does not. But the derivation from getting something modular is nicely described here, and there are some tricks to avoid this. So, but we can do the following. We take bilinear forms in derivatives. So I should start to say the following. What I'm saying about derivatives has nothing to do with the arithmetic group gamma. It will be completely independent of the group gamma. It will be something on the action of SPNR. So what I'm doing now, forget about gamma, because after all I could have reformulated this as just as a question of compatibility of actions, not in inserting the invariance. So therefore I start with two functions on H, holomorphic, and K and L some numbers. Maybe different from 0. And maybe for arithmetic, that doesn't matter. And we can explain this by the following. These denominators here remove this, and from F and from G you get a disturbing term zz plus d to the k plus 1, and by this difference we remove this part. So by starting by a pair of functions, we can get a bilinear differential operator which changes weights of k and l to k plus l plus 2. Okay, so yes, this is Rankin bracket. People call this Rankin bracket. Rankin-Cohen bracket, yes. Yes. And maybe now in Bordeaux. But this is not the end of the story. This is not just for SL2. Theorem by Ibukuyama, 1993, 99. Still okay. So still take K and L and Z. That is a polynomial representation. operator k rho still we start by scalar valued functions such that for all gamma in SP and R except finally many is it is non-vanishing. Well, I should have written here, should have multiplied everything by k times L, and then for certain k and L, this differential operator is 0. That would have been more appropriate, and in this formulation it is better to do like that. So you might again get annoyed why we start from scalar valued things, but we have to say this is some research going on presently to try to start from vector valued things. It is not so difficult if we start from scalar valued things. So the action here is scalar valued, and we can produce everything, every kind of vector valued thing. I mean, the extreme case is just to multiply f with g. And one has to say there are two things to be taken into account. One is the question of existence of such things. That can be done here by invariant theory, because you have to guarantee certain it's closely related to pluriharmonic polynomials again, and their existence is guaranteed by general theorems in invariant theory. This is one thing. And the other thing, which is a special concern of Ibukiyama, is the question to get explicit formulas. I mean, here I wrote down an explicit formula, but that statement you can make without writing down the formulas. And Ibukiyama has many papers on explicitly writing down these formulas. Okay. Yeah, and these differential operators are used also in many cases to construct new modular forms from given ones. But this is not so much my concern now. I have yet a different way to look at, maybe more importantly, construction. Well, do I take Hn? I take now H2n to C. Z1, Z2, Z2 prime, which is transpose, which is Z3, and that's now Z4 and H2n. Can be, you can use a Taylor expansion around Z2 is equal to any this is n by n matrix here. But the Taylor coefficients are functions of that 1 and that 4, and they will not be modular forms if f was a modular form. So but certain linear combinations of Taylor coefficients will be modular forms. And here again a theorem again by Ibukiyama. 1993. Maybe with some extensions here. Kn should be bigger or equal to some L, and this L maybe should be bigger than 2n. Then there exists dl rho, which maps holomorphic functions on Hn, H2n, these values in C, to holomorphic functions on Hn. This was 2n, this is n, and here we take a tensor product. So here we have the slash action by this So it's polynomials with derivatives evaluated at z2 is equal to 0. Such that for all a alpha b beta c gamma d delta so the things with a b c d are in SPN. The things with alpha, beta, gamma, delta are in SPN. All F DL, how did I call it? L row of F slash that L of this matrix here. Now this is a function on Hn cross Hn, yeah, because we have restricted to z2 is equal to 0. And now I take the slash action of a, b, c, d and take the slash row action of alpha, beta, gamma, delta. Now this goes with respect to z1 and this goes with respect to z4. So here and here. Yeah. So in particular, I will finish in a minute, if you start from a modular form of weight L, determinant L on H2n, you get a tensor product of modular forms on Hn for rho. Huh? Now this may look very complicated. Let me give you example. There is examples. Yeah. So you start from a function on H2 R minus L so it takes the second derivative of this variable for which you put things equal to 0 plus d these, when you apply this to a function on H2, they still depend on Z2, so you have to do this here. And this you can find in Eichler-Saguet's book, implicitly. It is not formulated in this way because it is written for Jacobi forms, and so the second variable here doesn't appear, only appears as an index in Eichler-Saguet. Why do I do this? Next time I want to explain the doubling method, that is, you start from a Siegel-Eisenstein series of degree 2n and restrict it to like this. But this restriction is not enough. You have to use these differential operators as well to get enough information, in particular to include the vector valued case. Yeah? And then we will end up by getting a lot of information about vector valued modular forms of degree n by using one simple function on H2n on the big space, namely the Siegel-Eisenstein series, which we restrict to these blocks and use these differential operators to extract even more information out of the Siegel-Eisenstein series. Okay, I think. Thank you.